Okay. All right. So I'm decreasing rate. So magnetic field, that's that variable. The rate at which it's changing is that. Okay. It's decreasing. Teslas per second. It's like dt. It's decreasing, so the rate's negative. Okay. So, so I'm looking for the acceleration on a proton that's at rest. In my brain, I'm thinking acceleration, force is equal to mass times acceleration. And so I'm going to, I know that so the EMF produced is the rate at which your flux is changing, specifically the negative, but I don't think I need to worry about that. There could be an N in there for number of loops, but it's just one area, so I don't have to worry about that N. So flux is equal to the field times the area. Okay.
Wait, so when you do, there was one that was like area, like it's like you take, like do you do one or two? Like, do you know what I'm saying?
Yes. At point A, you are going to see. Do you need to do a line integral for that? I think you just need the whole thing because it's just in that field. Yeah.
But there's something to do with the radius because the answers for like C and D are different. Yep. Otherwise, it would be the same.
No, so the answers for C and D are different because you do the line integral. The line integral determines how far away it is.
Well, like for BA, you do the whole A. Like 2 pi times 2 squared.
For all of them, I believe. Yeah. It's just the line integral that changes. Because the line integral is like the circumference of the line integers, which is why A and C have the same answer.
And point B. Yeah, because it's magnetic field is decreasing. All right, so I'm going to that's the thing I was teaching you, right? That's what I was thinking. That's what. Okay, so this is also equal to this. Okay, so this is what's going to be able to make the connection between this changing, the rate at which this flux is changing, the magnetic field is changing, and the force, because the force is just the electric field times the charge on the electron. You okay with that? Okay. So this, the path of integration for A, that's where the radius comes in. Okay. So electric field times 2 pi r, so that's going to be, in this case, 1 centimeter, is going to be equal to the rate at which magnetic field is changing. So the area is yes, I'm trying, I think, so we got area times dB dt, and the area, I'm going to tell me if I get this wrong. I'm going to say, sorry, pi r squared, but the r being
The radius for the point.
1 centimeter. Did I not get that?
No, it's one because the r's have to cancel because there's only one r when you calculate.
Electric field. I'm going to try it. Eraser in my back pocket. So pi r squared. So this is just your 0.5. So the electric field is going to be equal to r times 0.5 over 2. So do you get that? So 0.01 0.01 times 0.05 or 0.5 divided by 2. 0.025. Oh, that's just the electric field. That's not the answer. Yep. Okay, so that's 0.025. Yep. Okay. So, and then I take that, multiply that by the charge. So times, thank you, 1.6 times 10 to the negative 19th coulombs.
I thought it was 1.69, but
It's 1.60.
oh, 1.609.
That's right.
Okay.
Then divide by the mass.
And then divide by the mass. Oh,
Which
I
is
don't,
1.67 times 10 to the negative 0.7.
That one I know is on the equation.
They're both
27?
Yeah.
Okay. Ugly. Okay, so times 1.6.
So, Smiley, can you walk us through what you did in that question one more time?
Yep.
Well, let's make sure.
Daniel, you're still playing geometry, right?
I got.
I really don't think that. I think
He's actually
I
like.
think the ASC is
You do?
Daniel's insane.
Yeah, it'll take it.
Okay. So that's the mistake I made.
So I took the area enclosed. So where the discrepancy was, the example that I gave you before was, what about out here? That's where the area, the flux is. It's the flux. It's the amount of. It's the flux. It's the flux going through this point here.
It's the area enclosed. It's only the flux within the circle.
Yes.
Which is why, like, the whole circle around.
That's more than.
There's not magnetic field.
Right.
In that whole, like,
So
space.
if you did this, if it said, "Hey, out here," there would still be an electric field. Okay. The flux would the flux that you calculate would be just in the 2 centimeters. It wouldn't go all the way out to 4 centimeters.
So.
Right. So do you see the difference there?
Yeah.
So B would just not experience.
Correct. B does not experience. Sam.
I see the difference there between inside and outside. So when we are inside, do we use the whole circle?
No.
You just use a circle around a radius that we're given.
Because that's the area of the flux.
Okay.
Like the flux that we're trying to calculate is this area.
Understood.
Okay. Good with that? Okay. So does that help? Are we good with the rest of that? It looks like you're just doing that repeatedly. Okay. So in Okay, when you take the derivative of this, you have to do chain rule. So, okay, usually in this class, it's one or the other. Either you have a constant magnetic field and the area is changing. Okay, for example, if you have your simple model of your generator and you're pulling it this way, okay, the magnetic field is constant, but the area is changing. And the way you figure that out, and this is so common of example problem, this area is changing, this length is staying fixed, but this dimension is changing, so the velocity of this is so the length times the velocity is the rate at which your area is changing.
There's a problem like that on it.
Until they make it
No.
up.
Except it was a diamond that was getting pulled.
It was. I was like, oh, this will be bad, and then yeah.
That was bad. Yep. Okay. So, are we good? Okay. Tim.
This is not really the math.
But
for the AP test, will we have to design a lab like we did last year?
Oh, that actually doesn't need
No, not as vividly. No. Okay, good. Next one. Oh, this one. All right, over here. Ooh, that's a lot of reading. All right, electromotive force around loops, that is a distance.
That relates to residential powers.
Oh, this is, okay, this is what we just talked about. This is outside of the,
You just don't have to plug in for force. You just use the integral ES.
yeah. So is everybody good with, is everybody okay with this? We just talked about this in the previous example. You're outside, so the flux, the rate of change in flux, the area that you use is just this inside part here. You don't use the radius where you're trying to evaluate it. You use the radius of where you're trying to evaluate for the line integral.
Yeah, we're good.
Good? What?
Oh, wow.
We are. Okay. Okay, so this is this. So you've got a fixed area. So the rate at which flux is changing, and it's one single loop, this is going to be equal to your area times the rate at which your magnetic field is changing. So you just take the derivative of this, okay, multiplied by the area. Okay, and that gives you your induced EMF, your voltage, and
loop has a resistance.
And oh, it gives you the resistance. Beautiful. Just use. Well, they could have given you the resistivity, and then figure out. That's where I thought they might have been going. If they gave you the resistivity, then the resistance is equal to resistivity. Yeah, or the radius, yeah, something of the wire.
That's too much work. Skip it. Not worth the 2 points.
Okay.
This has, I think this one has the least amount of text.
Did it? Oh, yeah. Okay, so are we good with that? And then you just plug in T different times. Okay. uniform 60. Okay, so you need to, use trig. A uniform magnetic field 60 degrees from the verticals increased.
What is the axis of coil? I feel like I messed that up.
With its vertical axis. To rest with its vertical axis. So its axis is like this, where the okay, so the axis is this, which is vertical. Okay, so here's how my brain works. So technically, what they're going to write on the equation sheet is this. Okay. Yes. Because personally I hate this, but it works out like it's. I get it why they do it, but conceptually it's not helpful. Because what you need to do is find the component of this magnetic field that is perpendicular to this surface. And dot products find the things that are parallel, but the way they justify that is they make the area vector orthogonal to, which is just.
That makes so much sense, Smiley. That makes so much sense.
Okay, well you can go with it.
From multi-V, that makes so
Yes, I mean I get it why they do it.
Multi-V defines planes with a vector.
Yes, it is crazy. All right, so you find you just want the stuff that's perpendicular, so you're going to use cosine. So magnetic field times the cosine of theta.
You're trying to find the flux.
No, I want the part that's perpendicular. This.
Perpendicular to the circle.
Yep.
Oh, I thought you meant perpendicular to the vertical line.
Oh no, sorry, parallel to the vertical line.
Oh wait, I need to do that too.
Okay.
Wait.
So.
I got this question right.
So the rate at which this is going, I'm assuming it's a constant change. So it's just change in magnetic field over the change in time. Vertical final minus initial. Man, Emma, your words are so uplifting. Okay? Good? 60.
Okay.
Smiley, what's that equation that you're using at the top there?
Just the change in, it's just the rate of change.
Yeah. Oh,
okay. The average rate of change.
Okay. Yeah. So you're using that for dB. Okay.
Yep.
And then EDS equals integral of EDS equals whatever.
Yeah, I don't think you have to do that here. You just so this is area, which is the rate of change of flux, which is equal to the EMF induced, and that's all you're asking to find.
Oh yeah.
What's that equation called? The little the EDS is equal to change in flux. Is that Faraday's?
It's Faraday.
Faraday's.
Okay. It's like a fuller expression of Faraday's law.
Multiple times they were like, recall Faraday's law.
Yeah. So Faraday's law is this. This is what you had last year. We tacked on this year.
It was probably delta flux over delta T.
It was. Yeah.
What amperes then?
Amperes is the current through.
The loop thing.
Yeah,
Okay. And that says how much magnetic field will be produced by current. Okay. Ooh.
The one where you can do 2/3 of it without actually doing any math. If you pay attention.
Yeah. That was a good time.
Okay.
The second one. The first one. Yeah.
Do I need the first?
Go to the graph. Figure 2 on the thing is the graph.
Okay.
No, I didn't do it. Oh,
I'm so lost.
yeah, that would have been times when. And then I picture. Oh, this helps so much.
Okay. So, folks, this derivation, finding you can memorize the solenoid. Actually, they give it to you on like the magnetic field strength in a solenoid. They give that to you, but you need to know how to derive that. Like a free response, they will totally like use Ampere's law to prove magnetic field of a solenoid is what is it? Mu naught n I. Riley. Okay.
Would that be lowercase sign or capital?
Lowercase.
Thank you.
Okay. So here is your Riley, when you're set up, ready to go, so let me know. So here's your Amperian loop. You ready? This is key. Did I tell you how many? Yes. So
Oh yeah.
okay. So you box the whole thing. If they give you like an infinite thing, but they said there's like 5 of those loops in like 4 centimeters or something, just take that as 5. Okay. So you don't have to incorporate the whole thing, but in this case, I'm just rolling with it here. So your Amperian loop. Ugh. So this is magnetic field solenoid. This here is only where you're going to have magnetic field that's parallel to the Amperian loop, the path of your integrating, okay, the line integral. Here, the magnetic field is going perpendicular, and here, the magnetic field is 0 out here ideally. Okay, so that segment there, the length of that is ds, the integral, like that's just straight through. Okay, and then this, and then the I through is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 wires times current. 100. Good, Riley? Thank you.
Smiley, just intuitively.
Yeah.
Is the resistor affecting that at all? What resistor? It said that there's a resistor on the outside.
There's a resistance. We're finding the current in the loop outside.
Okay.
Oh.
So that does.
Mr. Smiley, so then number of terms of L is equal to N. I don't know the color I've got.
Where I'm like,
The L is, this is 12 centimeters. This would be 100.
But I'm talking without numbers.
Oh, sorry.
Without values.
Yeah.
It would just be, so big N is 100.
capital L. Yep. Okay. Is everybody good?
Yes.
How to set that? Like that's a thing. Tighten. I'm going to put you back there. Okay. All right. So to find the current, I'm going to find the EMF. So there's one loop. My Amperian path is going to be that.
Yes.
Okay. So I've got my electric field times 2 pi by 2 centimeters. Okay, meaning the radius of this, 2 centimeters. Okay, is equal to current times my resistance. They told me the resistance. Is that right? 0.19 ohms is equal to the rate of change of that. So that is my area times the rate of change of that. So the area is going to be pi times 0.1. Oh, no, 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 no.
It would be 2
It's just 2 centimeters.
Well,
So 0.1 point.
2 centimeters diameter. So.
Area of the solenoid. This is my area where the flux is. Okay. So 0.01 1 squared.
That's the radius.
It's the
It's 0.4 centimeter.
this is 4 centimeters. So this this says because that's where the magnetic field is.
Well, the line angle is for the wire.
Yes.
Right. So it should more of a reading around.
That's why we put on the left and not the right.
That's what this is.
3 pi r pi d.
Okay. Good.
Yeah.
Circles that define my theory.
Okay, and then the rate of change. What are we changing here? Current is clock. Oh, I was like, where is that? That's what figure 2 is. Thank you. So you find the slope of this. Okay. So so the rate of change of current is negative 40 amps per second. So how that gets incorporated, so we know the magnetic field of a solenoid is equal to mu naught N over L times I. Yep.
Yeah, because capital N is the number of loops.
This ratio becomes lowercase n. Okay. So the rate at which this is changing is just the rate at which current is changing times that constant stuff. Sorry, I get, and do you get?
I'm gonna have you go back for just a second.
Yep.
Command.
As usual for my questions. How did you know to use Ampere's law versus Faraday's? Like, what are the two situations that you use?
So they gave me this. So Ampere's law is used to figure out the magnetic field by a current created by a current. Okay. Faraday's law is used to calculate the voltage or the electric field created by a changing magnetic field.
Changing magnetic field, which in this case is changing voltage created by that change.
Okay. Good with that? You're welcome. Everybody good?
Yeah.
Yes.
Okay. So as I'm going through it, what could I do to prepare? Like, I feel like the feedback is you're unprepared for this battle.
Yep.
What would have been helpful? Another week.
Well, like when we're doing the slideshow, I feel like it's all conceptual and we all get it, and then when it comes to actually doing it, it's completely different.
Okay, mastering. I feel like mastering it takes what we know and just like distorts it. Makes it so much harder than it actually is.
It makes us feel confused.
For like E&M practice.
Say it again.
From the AP, like more AP fears, not E&M.
Okay. So what this is getting you ready for is the multiple choice.
What?
No. Listen. It's harder. It's harder than the multiple choice. But like I can give you plenty of free response questions. And you'll get that before you hit. You'll be well versed on the AP options they've got for you. But the multiple choice are just like tidbits, and like it's just snippets here and there. It's conceptual, but it's also quantitative, and that's kind of why I threw you in the deep end. Sam.
For me, what would have been helpful, because every mastering, I felt like I was just like kind of thrown into it. Like, because we did all the conceptual stuff and then the mastering is everything else.
Yeah.
So if you could do a mastering question, like, and post it, like I mean, I guess that gives us the answer, and that's kind of not the point of it, but like, I just felt so blind.
I get
that, like, felt like I was looking up the answer anyway. Like,
okay.
I get what Sam's saying here, in that I feel like I often learn a lot through the mastering just by like teaching myself through it.
Yep.
And I think I don't know how that is for everyone else in here.
Like you look up the answer and you go backwards.
No, like
No.
I go through and I bang my head against the wall until I figure out what works, and then I draw conclusions from that.
Are you saying that's a bad way to do it or a good way to do it?
Fine. By the end of the mastering, I have a good understanding of it.
Okay.
At least I thought, until you said that the area was not that, which is where sometimes the issues come. But I think for most of us, it would be helpful to get like walked through some of that in class, in that, like, because this is beneficial to understanding, to not have to draw conclusions, but to have you like straight up give me the conclusions.
Okay. Sam.
Part of that is my fault, because I don't start the mastering until the day before. So
I know.
That is also part of it.
I feel your pain. Like.
I feel like I literally like study the mastery to like try to figure everything out.
I'm fixing it now. Here we go.
Listen, if you're more prepared for college because of this class, I've done my job. At least part of my job. All right. So is one wire RC. Oh. Wow. Look at that. Capacitors charged to a voltage is switched closed. Okay, what is the direction of the current in the loop? Okay, so current's gonna go this way. That creates a magnetic field.
Oh yeah.
Coming out Okay, it gets weaker as you go away from it. Yeah, this is pretty involved.
It's a 4 point. This is the one I was talking about.
There's 4 parts.
No, just 4 points.
Oh, that's it.
Yeah.
Man, that's rough.
Two of them are yes because you got.
All right. So time constant is equal to RC. What? Direction?
It's the direction.
Oh, in the loop. Sorry.
Yeah, I did the same thing and got it wrong.
Okay, my bad. So the direction of the current in this loop is clockwise. This guy, so it initially starts really strong, the current, and then over time it gets weaker. So the flux coming out is coming this way. It's getting weaker, so the change in flux is going this way. So the current, the magnetic field that's induced is there's an electric field and a current going counterclockwise in the gold loop.
Yeah, they could have said that.
They could have said that. Okay, so your current, that's something that starts high and goes down, is equal to your initial current times. I would memorize this.
Yeah, it's not super. There were multiple times where they almost forced you to derive it.
Oh yeah, I tried to do that so many times.
Like 2, 3, 4 times over.
Yeah, I think they did,
which is helpful.
That was a while ago.
Okay. So you've got that. Okay. Then magnetic field from a wire. This should be memorized, but you should know where it comes from. Okay. From a wire. Here's real quick. This is just real basic stuff. If you have a wire with current going through it, and here's our Amperian loop, certain distance R. Okay. So Ampere's law. Okay. And so through that is 2 pi R. So magnetic field by a long straight wire is equal to mu naught times I over 2 pi R. Okay. So this goes here. Current. And so we want, yeah. Sorry, focus. I'm not going to worry about the electric field. I'm just going to go for voltage. So the area is fixed. So I need the time rate change of the magnetic field. Y. So I'm going to take the derivative so that I can find the area of this. That's my area. Okay. And then this, I want to just take the derivative of this. Sorry. Then multiply by these constants. So this is, so my dB dt is equal to Ooh. Oh.
What?
That's ugly.
But you can just put RTA.
No, because your radius is changing.
Yeah. You have to do it. I think you have to do it integral for V.
Wow, 4 points, huh?
Yeah.
Yeah, and half of it
I
is
looked it up.
as I learned.
Saw the math. Because it said 4 points. I'm like, okay, I gotta be able to think of this. So I looked it up, saw the math. I'm like, I know what that's like.
No way. Yeah, you got to do the integral on this one.
Yep. That's what
Or you can say that you did 5 microseconds basically. That's what I did. I know.
Mostly confused cheating.
Yeah.
I think discussion I can use your way.
Wow. Yeah, so that's a good call. So 5 mic. Well, even though I don't know.
It's pretty close, Smiley.
Okay, did it work?
Yeah.
Oh.
It's like your rounding was a little bit off. Yeah, when it's not 0, it's just I of 0 works.
Okay, so if you had to do this,
Well, the initial current is just 20 volts over 2 ohms, and then it gets 10. And then you're like, all right, that works.
okay, so
Maybe that's how it's 4 points. These kids are gonna try so hard to figure this out, but they can just.
If you want to be even more accurate, you can take 10
Man.
minus
That's
So,
that's brutal.